Hiya. After the video about standing on the shoulders of giants, I realized that there's quite a conversation to be had about framing the problem. It's not necessarily straightforward. This is different than knowing what the problem is, but more along the lines of what are the fundamentals of the problem and what do I have to work with? A couple of disclaimers first. I'm going to use some examples from my current and past projects. I'm not going to tell you anything that isn't already publicly disclosed, but I will try to provide you some insight into why and how we got to the solution. As I mentioned before, also, full development of all of these ideas almost always takes a team. Even when I'm sharing with you something about my thought process in examples of how to approach the different steps of innovation. All right, so let's start with the artificial lung. Now, in this case, the overarching problem is to get gas exchange between two liquids while keeping the two liquids separate. Based on past experience, actually work we had done on the artificial kidney, we knew very early on, at the very start of development in fact, that the two liquids needed to be immiscible, like oil and water. At first, we tried to keep the two liquids on their own side of a channel, and we did careful math to calculate how much diffusion we would get. In reality, however, because there is no math that fully explains the behavior of such a complex liquid as blood, we didn't get as efficient a diffusion as we expected. And moreover, the two liquids didn't stay 100% perfectly separate. Eventually, we realized that we had framed the problem too tightly, and we were struggling to get a perfect solution. See, we had framed the problem as get gas exchange between two liquids while keeping the two liquids separate. But the actual problem, framed properly, is get gas exchange between two immiscible liquids and have them separate at the end. And it pretty much doesn't matter how you get to the end as long as at the end they are separate. Reframing the problem like that brought us a slew of potential solutions that we were able to work through quickly in the lab, because remember, the math doesn't quite explain the behavior well enough. And we could do this quickly in the lab based on all of our previous experience. Now we're poised for our next big change in the underlying science, to shrink the size of the diffusion chamber, and we're framing the problem in a slightly new way to help us get there. So back to the topic at hand. To find a solution to a problem, you need to be able to frame the problem, which is to state the problem and include in the statement what you have to work with. Bear with me while I walk you through another example. The conception of the OMBA system, on-the-move balance assessment. There's a video of this technology linked to my LinkedIn account. Now, in this case, the need was identified by a topic posted by the US Department of Defense. They wanted to be able to monitor the center of gravity and center of pressure while a person is walking. This is related to traumatic brain injury and the difficulty with balance and falling that some people experience long-term after a brain injury. The act of walking is essentially controlled falling. At each step, you sort of propel yourself forward and you bring your trailing foot forward fast enough that you can put it down before you fall. But any of several things can go wrong and end up with you on the floor. For example, if you don't bring your trailing foot forward quickly enough, or you bring it forward but you put it down too close to your front foot so your body's momentum overtakes it, or somehow your upper body moves sideways, throwing you off balance completely. These things can be studied in fancy rooms with many cameras like motion capture animation that they use in movies. But there was no practical way to monitor for these things when a person is walking out and about in their regular lives. Now, interestingly, in the topic that was published, they suggested a solution. Put accelerometers on each body part to calculate the position of each part. In an ideal world, that would work, but in reality, calculating position from an accelerometer is prone to error, specifically drift. After a while, the calculated position ends up being impossible, like someone with an arm that's 10 feet long. We know that's not right. But that, right there, is a key to framing the problem. We know something about the human body. Arms are a certain length, and they have a shoulder and an elbow, and we understand how those move. By breaking the problem down like this, we realized that we didn't need the absolute location of body segments in space. What we needed was the distance between body segments. For example, the distance between the wrist and the torso. And we can calculate posture because we know how the human body is likely to have bent the joints to get into that posture. The AMBA system did also use accelerometers, but in such a way that we stayed away from the fundamental issue, the drift problem. So in this case, the problem may have been calculate center of gravity and center of pressure in real time, but the useful framing of the problem became calculate whether someone is about to fall based on the position and trajectory of their body parts relative to one another. And by framing it this way, we could come up with a more robust solution than originally suggested. So, in conclusion, identify the problem and frame the problem down to the components. What do you have to work with? That might help you identify a direction to a solution.